Well, I suppose we could start in alphabetical order. We are working on a system for distributed key generation and threshold decryption called Fairview, which is a collaboration with SICA. So Dave can probably speak as to any parts that I miss, or perhaps parts that I don't even know about yet. One, it sounds like you've already covered, as you referenced in the slides, threshold decryption. I'll just note that the way we integrate closely into the consensus algorithm, in this case Tendermint, although the approach should generalize to any sort of like multi-phase BFT consensus, allows us to more or less avoid the one block delay. I mean, there's still latency insofar as the validator set, which is the same as this set which has to provide threshold decryption shares, in our case, has to like compute the shares and combine them. But because we can just put the threshold decryption shares for each transaction in the pre-commits in Tendermint, so in the last phase of the BFT consensus round, we can execute the transactions in the same block, decrypt and execute the transactions in the same block, even though the proposer, who has to propose before the pre-vote round, which happens before the pre-commit round, has to commit to an ordering of encrypted transactions by the time we get to pre-commits. If a block is finalized, because we have the same set for 2/3 of the quorum requirement to finalize the block and 2/3 of the share requirement to decrypt transactions, those two coincide. And so we can decrypt and execute the transactions in the same block in which they were committed.
Okay, maybe I can take the next one. Hi, everyone. This is Deli. I'm the co-founder of Automata Network. So for those of you who heard about us for the first time, we are building privacy middlewares for the apps across multiple chains using SGX and ORAM. So our team has several researchers who has been doing SGX research since 2014. And some of us were previously working at a security research lab in NUS, National University of Singapore. And just to let you know, before Automata Network, this research lab already had a few successful spin-off crypto projects, such as Kyber Network and Zilliqa. So under this context of MEV, we are actually developing a decentralized privacy middleware called Conveyor to help DEXs to minimize MEV. And also, if you happen to know that we actually also released a small free tool called mev.tags for people to inspect if they have been sandwich attacked previously. So our approach is we are using trusted hardware, TE or Intel SGX, whatever you think the term is, to try to just hide the transaction temporarily and determines the transaction orderings before it's published. And to preserve the maximum compatibility with existing blockchains, it will review the transaction only after the ordering is locked, decided and locked. So that means layer 1 block producer and also layer 2 sequentials we just process it as normal transactions, but they don't have the ability to change the order anymore. So this would allow us to directly work with DEXs on many chains and to protect existing users with a non-intrusive integration with them. So and maybe a little more details about it. So the ordering we are providing here is actually particular to it's very application specific. So we can even just provide a lot order only for the a particular trading pair, and we will have multiple trading pairs running in parallel. So it's kind of just a scalable way for us to support DEXs. And the other technique we are using is called oblivious RAM, which kind of directly enhances the privacy of trusted hardware, and it also raises the bar of breaking DEE through side channel attacks. So we know trusted hardware can provide these safe rooms or enclaves, but it actually doesn't solve all issues. For example, the traces left by these enclaves when interacting with the outside world could leak information. Even your data is encrypted before leaving this enclave. The access pattern that it reveals could be collected and learned by malicious node operators, and then used to infer the computation inside your enclave. So there have been papers that successfully apply these side channel attacks and also extracted private keys from TE. So it's pretty dangerous in some sense. So and this kind of attack involves many rounds of profiling, probing, and analyzing, and the sensitive information is actually reconstructed sometimes beat by beat based on the access pattern that were exposed. So maybe I can give an example of this. So if something looks like a duck and screams like a duck and quacks like a duck, then it probably is a duck. So if some observations of the access pattern could be associated with certain computation with very high probability, then the observer would know what you are doing, even you are using trusted hardware. So ORAM is trying to change the access pattern so that even the traces are observed, it will be useless because the access pattern will not make sense anymore to those observers. And this line of research actually has been there for several decades. And the idea is just to providing, kind of shuffle the access pattern, just doing more useless work, but it ended up just doesn't allow the observer to get any useful information from that. So yeah, so that's the kind of the technologies we are using to try to safeguard the privacy of the transaction orderings.
Okay, cool. Who's next?
I think I can go next. This is John from Secret Network. Secret Network is a Cosmos SDK-based layer 1 chain where every validator runs an SGX. And as a result, the privacy, as every validator runs an SGX, what happens is we can ensure that all contracts on the network are privacy preserving contracts. And the way this works is there's one chain that's one private key that's shared across all the validators that's generated within the SGX, or the trusted execution environment. And when a user is interacting with the network, they create a symmetric key by using their private key and the network key. And encrypted inputs are stored in the mempool. That's why no one can really see what's going on as to what the inputs are. And then validators take those encrypted inputs. They can decrypt them inside their enclaves because they have the network key. The computation takes place inside each validator's enclave, and then validators share hashes of the computation results on chain and form consensus based on those hashes. And assuming there's consensus, the state updates. The state's also always encrypted and stored on chain. So that's how Secret Network deals with front-running attacks. And we've had secret contracts live on our mainnet since September of 2020, and we have a functioning AMM that is front-running resistant since February of 2021.
Okay, cool. I guess throughout the panel, you'll probably have the time to go into detail to talk about how you differ from automata network. So let's see who's next. Dave?
Yeah. Hey, hello, I'm Dave. So I work on a project called Osmosis. And one of the things we're doing to prevent front running, as Chris mentioned, is working very closely with them, is to use threshold decryption. So Chris kind of summarized this earlier. So I think what I'll talk about instead as a brief overview is how we want to handle fair ordering, which I think is also an important question. So with threshold decryption on its own, a proposer can still try to get their transaction as the first transaction or the last one. So on top of that, we kind of imagine our take on fair ordering is not the same as kind of the Wendy or Equitas take. It's instead, which is this kind of this take on when something arrives in kind of imagined global mempool across all nodes. And instead, we're trying to take that everything in a block should ideally be treated as though it came at the same time. So the way you can imagine this for something like trades is then you can imagine you had a random permutation of the trades, and you take the average across the random permutation for how your trade would have been executed in sort of a batch environment. And then for things where you can't really white box like that, where it's not clear, like transaction sends, for instance, then you take a random permutation. So the idea is then, I summarize for orderings, then for things you can white box, like analyze, do some white box analysis as though everything came at the same exact time, or you have a random permutation of them all, which applies for trades on like Uniswap, for instance. And then for things you can't, take a random permutation based off of decrypted contents, and then do some other techniques to ensure that there's some decrypted content, there's some transaction content in there that the validator who's proposing the block doesn't control. Yeah, that's like what we do for fair ordering on top of like special decryption things.
Interesting. Yeah, I guess I'll have more time to go into details. Let's see who's next. Barry.
Can you hear me?
Yeah.
Hey, everybody. Yeah, so my take on MEV prevention is that there's two kind of approaches. The first approach is where you limit the amount of the group who are able to take advantage of minor extractable value. And that's where you see solutions like encryption and threshold decryption. And the second group is where the second approach is where you make it kind of impossible for you kind of randomly order transactions based upon you just randomly order them so that even if someone is kind of front running, you're not able to get as much value out of it. But there is a certain class of MEV that we're not really able to prevent with either mechanism. Like, for example, if someone is getting their collateral slashed, there's going to be MEV there. And even if you order the transactions randomly, someone is going to get that. And like this will actually produce this kind of weird incentive game where people are creating thousands and thousands of transactions because they just want to be the first one ordered by the block. So there's these weird kind of incentives that appear. And so that's my take. And maybe there's some interesting things to discuss about that.
Okay, cool. So Christopher went. Okay, so Jannik.
Yeah, I guess I'm the last one. Can you hear me?
Yeah.
Cool. So yeah, I'm from Shutter, and we're one of these projects that use threshold encryption to prevent front running. It's very similar to, for example, what Mikerah does. I think the general principle is very similar. The main difference is that we don't see this as a new layer 1 blockchain, but we try to interpret this as a more general technique that you can use and apply at different layers. And the first layer that we applied it on is very close to the application layer. So we implemented this as a kind of a smart contract system on top of Ethereum, so that users can send encrypted transactions to Ethereum, wrapped, of course, in a normal Ethereum transaction. And then those would be at some point decrypted and passed on to another smart contract, which would then be front running protected, basically. As long as they only accept transactions through this mechanism. Yeah, that's the main idea of Shutter at the moment.
Okay. So yeah, I think that is everyone. So I guess, yeah, from the introductions, everybody's working on different solutions, and they're meant to be deployed in different ways. So some are working on layer 1 solutions, and then others are working on drop-in solutions for developers as sort of a plugin. And so the main point of this question is sort of what are the pros and cons of using your respective technique at these different layers, a layer 1 or a layer 2, an application layer, however you'd like to answer that question. Yeah, I'll leave the floor to you guys to choose your order.
Okay, maybe can I start first? So yeah, our solution is actually so the pros about the solution is fully compatible with any kinds of layer 1 and layer 2, because we are really just trying to provide this solution as a plugin to the existing system, so that we can help the users and also the DEXs. And most important thing is we are not modifying any layer 1, layer 2 protocols. And also at the application layer, we are able to offer kind of different variants of implementations that balances between easier integration, better gas efficiency, or even higher fault tolerance. So for example, if you just need a very quick patch to get rid of MEV, so you could just build off a single trusted relayer that does a very simple FIFO ordering. that will just kind of solve that. But for sure, that introduces single point of failure. So maybe a more decentralized relay network that runs a little bit consensus algorithm to ensure the ordering is better. And in terms of the integration, actually, since we are just directly working with DEXs at the application layer, so they could just adopt this approach very easily, as it only needs to kind of acknowledge the ordering coming out from the trusted relayers. And also this kind of meta transaction approach also brings another quite interesting design point, where we can actually make the transaction gasless, and user won't need to pay in the native tokens for the gas fees. And also, since we have this great flexibility, our design also make it possible to work with other MEV solutions as well. For example, we can work with Flashboard in order to just ensure the order transactions are delivered without being kind of censorship by the miners. And talking about the cons, I think it's really about when you build this kind of relay network, it really takes time to fully decentralize your entire system. But actually, since we are using trusted hardware, each individual node in the system has a slightly different trust model than the just than a random node that hosted by anyone. So we sort of have a slightly better confidence on this TE node. So in that sense, even we're starting with a smaller number of nodes, the system overall is actually is also secure. Yeah, I guess that's my take on this.
I guess I can go next. For us, when you have smart contract privacy on layer 1, the things that you can address with that is like much more than MEV. Like you could have like NFTs where the content is encrypted, and you could get into like more subscription and content access or content monetization like use cases in the Web3, which to me is very, very exciting. And also like building things are easier. But then the problem is then, you know, you have to build a new ecosystem and have new people build applications on this new layer 1 rather than plugging into another network. To me, that's like that's the big trade-off. And I think one thing that we are doing more and more is to explore some sort of like an operator model, whereas, you know, in order to target someone who's on Ethereum and like, you know, just like a simple use case, say want to do a mix, like one thing that we are working towards is how to allow the user to do that just with a MetaMask transaction rather than getting into the whole Cosmos ecosystem, like wallets and tooling. And I believe like that will be something that will allow us to target more people, where like, you know, we can have the user get a key from the secret network through the help of an operator, and then when they're making their Ethereum deposit transaction, they can also like, you know, create an address that where they want to get their funds back. That address can be decrypted in secret network. I guess that's similar to what you have been mentioning, Deli, and then, you know, sent back to Ethereum to just like, you know, make a new transaction. But that mean that like, you know, may not be as exciting in the MEV and DEX cases because it does add some latency.
We're also building, Anoma's also building a layer 1, and I would agree with the primary disadvantage of simply adoption from zero or building an ecosystem up from scratch, although I think some of that can be mitigated with good interoperability protocols. The other point I would note, specifically with relation to MEV, is that it seems to me like for some of the protocols involved, which use randomization or which use threshold decryption in ways which are you know, where there are like a bunch of transactions being grouped together and somehow combined, as Dave was mentioning, or being randomly reordered, there's a little bit of a sort of network effect, or like the larger the set is, the better the like guarantees or the better the kind of unpredictability individual transactions have. And it seems to me that's easier to achieve in practice when you can make it the default in a system, as we can much more easily do at a layer 1 than perhaps in kind of an add-on solution, just because the whole system can be architected to integrate it as like the default pipeline for submitting transactions, and we can change dynamic consensus rounds like I mentioned. So it's very easy to achieve a kind of holistic integration such that end users can really use threshold decryption without knowing it, and such that it's so easy that even transactions which don't need it and probably aren't going to want to pay additional costs either in gas fees or in user experience to get it, can get it for free, and thus contribute to the public good of more transactions being randomly reordered or whatever.
I guess I can go next. I think Chris summarized this pretty well. I guess I do want to say on the point of like MEV resistance tactics, I don't think there's actually a meaningful difference in pros and cons between L1 and L2. Really, what you're doing is you control your own like chain, your own consensus, and L2, or really rollups, really just means that you have some data that needs to be posted to ETH or whatever base chain, and some priority for like how getting transactions from ETH onto your chain. That's not really like an MEV concern. That's like a fund transfer thing, which didn't really have too much MEV, that really had like latency and censorship resistance concerns. So I think the key questions to ask is just your own chain, like L1, L2 is one category versus the app layer. And then for something like threshold decryption, the guarantees actually differ a lot here. Actually, really for all the mempool privacy techniques, except SGX. Oh, so I guess mempool of encryption and threshold encryption. Sorry, time lock encryption and threshold encryption. The guarantees differ a decent amount. Like, because you're doing in the app layer, to get these strong guarantees, you kind of have to make your own subset of the chain that's only taking in transactions from this encrypted layer. Here, otherwise, you get these like issues where, since the decryptors can never guarantee their transactions going to get like when it's going to get included, they could broadcast the decryption, and then if there was a path for someone who's not using decryptions to get the transaction in first, they do is they'd see the decryption being broadcasted over the P2P layer here, and then they front run that before the decryption gets posted on chain, then defeating the point. So it's actually, you have to, so when you're in the app layer, it's actually pretty hard to like, you have to kind of make your own subsystem, which is not going to be interoperable with the rest of the ecosystem. So I think that's like a key difficulty you have with really these mempool privacy techniques when you're at an app layer versus your own chain.
Yeah, sorry to interrupt you, Deb. I completely agree with what you're saying. That was the point that I was planning to make, and maybe to drive the point home, just to drag it out a little bit more. So the example here is that, okay, if you take Uniswap and you say we want to make a private version, we want to make a MEV resistant version of Uniswap, there's always going to be a place where the MEV resistant version goes to the smart contract to tell it these are the orders to place, and at that point you're able to front run. And this is the concern, that you end up just building everything in a silo, where you have like front run resistant Uniswap, and then you have Uniswap, and then you have front run resistant Compound, and then you have Compound. They can't really be interoperable between each other, and this is a big concern.
I guess I definitely agree with these concerns. That's also the main issue that we see, that this application layer front-running protection breaks composability in some sense. The reason why we still started at there is that it's just much easier to implement, and you can just focus on this particular problem of front-running protection, and you don't have to worry about all the other stuff. I mean, building a new blockchain is very hard. Building a new layer 2 is very hard. It takes a long time. So this is one reason why I think it makes sense to start there. And the other reason is, I think it has already been mentioned that it's the problem exists at the moment on layer 1 for many applications, and it doesn't really help them if there's a MEV or front-running resistant layer 1 or layer 2 somewhere else, if the application is on that layer that is not protected against this. So that's the two reasons I see for in pro of application layer.
Just, I guess, to like build upon this is like, depending on the application, you might be willing to like take some amount of, I guess, latency. So I guess asking you guys for your respective techniques, do you think some categories of applications are better for, are like best suited for your technique, or is there another technique that's like probably better, or maybe you think like your solution is good for all techniques? Sorry, for all applications. Any thoughts?
So I think a lot of the difference is based on the security assumption you're willing to take. So like, I don't know, I've been working on Tendermint things for years now, where in Tendermint, it's proof of stake algorithm where you say, I trust that over that like kind of 2/3 of this validator set is honest, but then I can detect their faults, and then if they commit some fault, slash them. And if you're willing to take that assumption, then I think the threshold decryption like security is works for like all the kind of really all applications I can think of, which are kind of siloed to one chain. Then you do have some like cross-chain concerns, but these are really inherent to all of the techniques. And so I think the reason I think like SGX becomes interesting for like when you want more than just like MEMP level encryption, but you then take the cost of like what happens when SGX breaks. Similar time lock is like I think interesting if you're willing to make hardware assumptions, but not these multi-party assumptions that you typically do in proof of stake. So I think it's really around the security assumption for time lock versus threshold. And then for SGX, it's like, well, okay, we're taking the lower security because it's cost to break one SGX, and we're instead pivoting to like, okay, well, here, what else can we do on top?
I think like my argument on that point is that like it's a different trust assumption. If you're trusting the majority of the chain to not do something that can potentially get them slashed, it's very different from trusting the majority of a chain to do something that they can never be slashed for. You can never prove that they did this. So there's no punishment for the validators if they kind of front run people. There's no way to even know that. Well, you can kind of know, but not really. But yeah, that's sorry, definitely.
Yeah. Oh, I spent agreed. I spent a while trying to think about this. Like, to what extent is this slashable? And I feel like the best way to get slashing abilities is to have the decryptor shares or the decryptors be in do the decryption work in an SGX. So that way they're still forced to be behaving the protocol correctly. Hey, but you still everyone only needs a cryptographic assumption to like know that their protocol was done correctly. But then it's as it depends on depth. So it's like, okay, well, now you need to break trusted enclave and break cryptography and break this 2/3 assumption. But yeah, agreed. This is definitely hard.
I mean, that there's no solution to that problem.
Yeah.
I mean, if there's an offline collusion attack, there's no way you can know it.
Well, what you need is you want to be able to have a defector report. So like in proof of stake, the reason this is we can do double sign protection is that a light client at the end of the day needs to get the double sign a different signature than the rest of the world, and this can be reported. So with front running, the problem is that only the validators actually got these decryption shares. So to get a similar level of guarantee, you'd need that any member of the validator set can defect and prove that, hey, look, this cabal tried to decrypt something when they shouldn't have.
Okay, I understand. Yeah, I think.
So I don't know how to actually do this without like more assumptions.
Interesting point, but I don't want to take all the time. But let's discuss another time.
And I think there's about 5 minutes left. So yeah, if you want to answer this question, or we can quickly go on to the next question. So I'm going to take that as we can quickly go over to the next question. So yes, the last question is, we're all dealing with either hardware assumptions, like SGX failing, or trust assumptions such as some quorum of nodes being honest, or at least incentivized. So how do you guys handle failure scenarios for your technique? And if so, like how does it affect the user? How can they recover?
So as already has been mentioned, it's very hard to prevent these key shareholders to collude with each other. And therefore, I think it's very important to make sure that they're well incentivized to not do this, mainly by having a lot of them. Because if there's a lot of shareholders, they will. It's much harder to collude, and it's easier for a single person to defect and notify the world about this. And the other way I think this should happen is that they are selected in a good way. So not just randomly, and not just the spot shouldn't be sold to the highest bidder, or that's at least what we're trying not to do, but instead select them from different organizations, from different sets of people, to make sure that they're not all not a single person. And lastly, to give them very long-term incentives, so that they have a financial incentive for the system or for keeping the system honest, and keeping the system keeping users trusting the system, kind of. And to do that, we probably want to have a kind of DAO that does the selection process, because it's very subjective, and you can't really write a cryptographic or economic protocol to do this.
Well, I would quibble with that a little bit. I mean, I think in the case of proof of stake systems, you have already a naturally incentive aligned group of participants in the validator set who are, because they're staked, aligned in some sense with the long-term success of the protocol, and who potentially have sort of out of band or chain external reputation on the line. Plus, they have the ability, if they are able to coordinate and collude in large enough groups, to commit more serious faults, potentially, than extracting MEV. So it seems to me like that's a case where there's a group that already exists, and you wouldn't need a separate selection process.
I think on that point, I kind of think about the kind of validator set as this like economic group, and this is a group that are selected based upon whoever is able to make the most profit from what they're doing. And I see like exploiting this kind of minor extractable value opportunities is just like another potential revenue stream for them. Like you've seen this on Ethereum when the Ethereum miners started en masse to use flashbots or fund running methods to increase their rewards. And I'm also super worried about the stakers on Ethereum doing this when we move to proof of stake. And it seems like just such a natural thing for them to do. I agree that like having these mechanisms in place will like some of these mechanisms will reduce the amount of money they're able to extract, but I feel like they will get more and more sophisticated because that's just how they make their most money. That feels like the natural place for them to be.
For us, because of the hardware guarantees, this is like assuming the valid. I mean, side channel attacks are going to be expensive because you have to pay gas, and then actual physical way to hack the TEs is like assuming most of these run on data centers is not very, I think, practical. And so that's how we think about it. But like worst comes to worst, like you end up with exactly in a normal blockchain kind of scenario.
Okay, cool. So I think that ends this panel. I'd like to thank everybody for taking the time to answer these questions and for going through the trade-offs on your respective techniques. I guess Tina can take the floor.